Merhaba arkadaşlar, günaydın. Umarım iyisinizdir. Geçtiğimiz haftalarda, özellikle son 2 hafta proseslerden, ardından da threadlerden, thread modelinden bahsettik. Artık genel olarak bu konseptlere hakim olduğumuz için bu konseptleri kullanarak kaynakların nasıl paylaşılacağı konusunda giriş yapmamız gerekiyor. Ve ilk olarak CPU time'ın daha doğrusu genel olarak işlemci kaynaklarının prosesler, threadler arasında nasıl paylaştırılabileceği konusunda konuşmaya başlayacağız. E, Eğer sorunuz yoksa doğrudan başlıyorum. Var mı sorusu olan? Okay then. Let's start to discuss about CPU scheduling. CPU scheduling is the basis of multi-programming operating systems. By switching the CPU among processes, the operating system can make the computer more productive. In this chapter, we are going to introduce basic CPU scheduling concepts and present several CPU scheduling algorithms. We also consider the problem of selecting an algorithm for a particular system. Last week, we discussed threads to the process model. On modern operating systems, it's kernel-level threads, not processes that are in fact being scheduled by the operating systems. However, the term process scheduling and thread scheduling are often used interchangeably. In this chapter, we use process scheduling when discussing general scheduling concepts and thread scheduling to refer to thread-specific ideas. Similarly, in the first chapter, we describe how a core is the basic computational unit of the CPU and that a process executes on a CPU's core. However, in many instances in this chapter, when we use the general terminology of scheduling a process to run on a CPU, we are implying that the process is running on a CPU's core. Okay, so we can use the CPU's core instead of CPU. In a system with a single CPU core, only one process can run at a time. Others must wait until the CPU's core is free and can be rescheduled. The objective of multiprogramming is to have some processes running at all times to maximize CPU utilization. Actually, the idea is relatively simple. A process is executed until it must wait, typically for the completion of some I/O requests. In a simple computer system, the CPU then just sits idle. All this waiting time is wasted. No useful work is accomplished. With multiprogramming, we try to use this time productively. Several processes are kept in memory at one time. When a process has to wait, the operating system takes the CPU away from that process and gives the CPU to another process. This pattern continues. Every time one process has to wait, another process can take over use of the CPU. On a multi-core system, this concept of keeping the CPU busy is extended to all processing cores on the system. Scheduling of this kind is a fundamental operating system function. Almost all computer resources are scheduled before use. The CPU is, of course, one of the primary computer resources. For that reason, its scheduling is central to operating system design. The success of CPU scheduling depends on an observed property of process. Process execution consists of a cycle of CPU execution and I/O wait. Processes alternate between these two states. Process execution begins with a CPU burst that is followed by an I/O burst which is followed by another CPU burst, then another I/O burst, and so on. Eventually, the final CPU burst ends with a system request to terminate execution. The durations of CPU bursts have been measured extensively. Although they vary greatly from process to process and from computer to computer, they tend to have a frequency curve similar to that shown in this figure. The curve is generally characterized as exponential or hyperexponential with a large number of short CPU bursts and a small number of long CPU bursts. An I/O bound program typically has many short CPU bursts. A CPU bound program has a few long CPU bursts. This distribution can be important when implementing a CPU scheduling algorithm. Based on these frequency graph, we can choose the right scheduling algorithm, or we can design the right scheduling algorithm. Whenever the CPU becomes idle, the operating system must select one of the processes in the ready queue to be executed. The selection of processes is carried out by the CPU scheduler, which selects a process from the processes in memory that are ready to execute and allocates the CPU to that process. CPU scheduling decision may take place under the following four circumstances. The first one, when a process switches from the running state to the waiting state. For example, as the result of an I/O request or an invocation of wait for the termination of a child process. So this is the first one, when a process switches from the running state to the waiting state. The second one, when a process switches from the running state to the ready state. So for example, when an interrupt occurs, so that process is not waiting anything, but we have to move that process from running state to ready state. Third one, when a process switches from the waiting state to the ready state. For example, completion of an I/O operation. In that case, that process has to be moved from waiting queue to the ready queue. And the last one, when a process terminates. For situations 1 and 4, which is switch from running to waiting state and terminate, there is no choice in terms of scheduling. A new process, if one exists in the ready queue, must be selected for execution. But there is a choice for situations 2 and 3. When scheduling takes place only under circumstances 1 and 4, we say that the scheduling scheme is non-preemptive or cooperative. Otherwise, we can say that it's preemptive. Under non-preemptive scheduling, once the CPU has been allocated to a process, the process keeps to CPU until it releases it, either by terminating or by switching to the waiting state. Virtually all modern operating systems, including Windows, macOS, Linux, and Unix, use preemptive scheduling algorithms. Unfortunately, preemptive scheduling can result in race conditions when data are shared among several processes. So consider the case of two processes that share data. While one process is updating the data, it's preempted so that the second process can run. The second process then tries to read the data, which are in an inconsistent state. So this issue is called as race condition, and we are going to explore, we are going to discuss these conditions and the solutions for that conditions in next chapter. Another component involved in CPU scheduling function is the dispatcher. The dispatcher is the module that gives control of the CPU's core to the process selected by the CPU scheduler. This function involves the following steps: switching context from one process to another, switching the user mode, jumping to the proper location in the user program to restart or resume the program. So the dispatcher should be as fast as possible since it's invoked during every context switch. The time it takes for the dispatcher to stop one process and start another running is known as the dispatch latency, and it's illustrated in this figure. So we are executing P0 and we want to execute P1. So first of all, we have to save the state into process counter block 0 for process 0, and then restore states from process counter block 1 for P1, and then we can start to execute P1. So we have a time here. We need some time here, and it's called as dispatch latency. Okay. Different CPU scheduling algorithms have different properties, and the choice of a particular algorithm may favor one class of processes over another. In choosing which algorithm to use in a particular situation, we must consider the properties of the various algorithms. Many criteria have been suggested for comparing CPU scheduling algorithms. Which characteristics are used for comparison can make a great difference in which algorithm is decided as the best algorithm. The criteria include the following: CPU utilization, throughput, turnaround time, waiting time, and response time. Let's start with CPU utilization. We want to keep CPU as busy as possible. Conceptually, CPU utilization can range from 0 to 100%. In a real system, it should range from 40% for a lightly loaded system to 90% for a heavily loaded system. The second criteria is throughput. If the CPU is busy executing processes, then work is being done. One measure of work is the number of processes that are completed per time unit, called throughput. For long processes, this rate may be one process over several seconds. For short transactions, it may be tens of processes per second. The third one is turnaround time. From the point of view of a particular process, the important criterion is how long it takes to execute that process. The interval from the time of submission of a process to the time of completion is called as a turnaround time. Turnaround time is the sum of the periods spent waiting in ready queue, executing on the CPU, and doing I/O operations. The total time called as turnaround time from beginning the execution of a process to terminating that task. The fourth one is waiting time. The CPU scheduling algorithm does not affect the amount of time during which a process executes or does input-output operations. It affects only the amount of time that a process spends waiting in the ready queue. Waiting time is the sum of the periods spent waiting in the ready queue. And the last one is response time. In an interactive system, turnaround time may not be the best criterion. Often a process can produce some output fairly early and can continue computing new results while previous results are being output to the user. Thus, another measure is the time from the submission of a request time, is the time it takes to start responding, not the time it takes to output to the response. So we have another criterion. It's called as response time. And these are the criterions we are going to use to select our scheduling algorithm. So based on that criteria, it's desirable to maximize CPU utilization and throughput and to minimize turnaround time, waiting time, and response time. From a good algorithm, we want to get that maximization of CPU utilization and throughput, and also a minimization of turnaround time, waiting time, and response time for all processes. In most cases, we optimize the average measure. However, under some circumstances, we prefer to optimize the minimum or maximum values rather than the average. For example, to guarantee that all users get good service, we may want to minimize the maximum response time. So instead of minimizing the average, we can focus on a minimal value or maximum value for one of that criterion based on our circumstance. Okay, let's continue with the scheduling algorithms. CPU scheduling deals with the problem of deciding which of the process in the ready queue is to be allocated the CPU's core. There are many different CPU scheduling algorithms. In this section, we are going to describe several of them. Although most modern CPU architectures have multiple processing cores, we describe these scheduling algorithms in the context of only one processing core is available. That is a single CPU that has a single processing core. For that reason, the system is capable of only running one process at a time. To understand the basics of the algorithms, we are going to consider that we are going to employ these algorithms on a single CPU that has a single processing core. So we're going to start with first come, first served scheduling. By far, the simplest CPU scheduling algorithm is that, the first come, first served scheduling algorithm. With this scheme, the process that requests the CPU first is allocated the CPU first. The implementation of the first come, first served policy is easily managed with a first in, first out queue. When a process enters the ready queue, its process counter block is linked onto the tail of the queue. When the CPU is free, it's allocated to the process at the head of the queue. The running process is then removed from queue. The code for first come, first serve scheduling is simple to write and understand because we have just a first in, first out queue. When the CPU is free, we are going to get the head of the queue. When we want to add a new item to the queue, we are going to add it to end of the queue. On the negative side, the average waiting time under the first come, first served policy is often quite long. So consider the following set of processes that arrive at time 0 with the length of the CPU burst given in milliseconds, P1 24, P2 3, and P3 3. So we are assuming that we have 3 processes and they arrive the ready queue at time 0 at the same time. And the burst time of process 1 is 24 milliseconds. The burst time of P2 is 3 milliseconds. And the burst time of P3 is 3 milliseconds again. If the processes arrive in the order P1, P2, and P3 in that order, and are served in the first come, first served order, we get the result shown in this Gantt chart, which is a bar chart that illustrates a particular schedule like that, including the start and finish times of each of the participating processes. So the waiting time will be 0 milliseconds for process 1 because we are going to start to execute process 1 at time 0. So the waiting time for process 1 will be 0. But the waiting time for process 2 will be 24 milliseconds because process 2 has to be wait until the process 1 terminates. For that reason, that means, okay, they had arrived at the same time, similar times, but in the order P1, P2, P3. So we are going to serve that resource based on first come, first served. So we have to start to execute P1. So this is a non-preemptive algorithm. That means we have to wait until the termination of process 1. After the termination of process 1, we can get the next process from the ready queue, which will be P2. So that means P2 has to wait 24 milliseconds to start the execution. So based on that approach, P3 has to wait 27 milliseconds because it has to wait the termination of process 1 and the termination of process 2. So process 3 has to wait 27 milliseconds to start the execution. So based on that, the waiting time for P1 will be 0, for P2 will be 24, and P3 waiting time for P3 will be 27. So based on that, we can get the average waiting time. We can sum that waiting times and over the number of processes. So in that case, we have 3 processes and their waiting times will be 0, 24, and 27. We're going to get sum of them and we're going to over that number to 3 and we're going to get 70. So based on first come, first served scheduling algorithm and assuming that we have processes P1, P2, P3, and their burst time will be 24, 3, and 3 respectively in that order. So based on that, we can directly say that the average waiting time for this set of processes using first come, first served scheduling algorithm will be 70. Okay? Any question? Actually, it's a very simple algorithm. Okay, then. Okay, assuming that still we have the same processes, P1, P2, and P3, and their burst times are 24, 3, and 3. But in this case, we are going to assume that the processes arrive in the order P2, P3, and P1. So the results will be as shown in that Gantt chart. The average waiting time is now 6 plus 0 plus 3 over 3, so 3 milliseconds, because the first process will be P2, so the waiting time for P2 will be 0, waiting time for P3 will be 3, and waiting time for P1 will be 6. Based on that, the average waiting time will be 3 milliseconds. Thus, the average waiting time under the first come, first served policy is generally not minimal and may change substantially if the processes CPU burst times can differ greatly. So still we are using the same algorithm. We are executing, we are running, we are employing that algorithm based on the same processes, but we just change the order of processes. So based on that, the waiting time changed from 17 to 3. Actually, I'm considering the average waiting time. So there is a convoy effect as all the other processes wait for the one big process to get off the CPU. If the first process you start to execute is a very big process, if the burst time of that process is greater than the others, so that means you had created a convoy effect because the other processes has to wait the terminate of your big process. This effect results in lower CPU and device utilization than might be possible if the shorter process were allowed to go first. Note also that the first come first served scheduling algorithm is non-preemptive. Once the CPU has been allocated to a process, that process keeps the CPU until it releases the CPU, either by terminating or by requesting an input-output operation. So we have to wait the process leave the CPU preemptively. The first come first served algorithm is thus particularly troublesome for interactive systems, where it's important that each process get a share of the CPU in regular intervals. It would be disastrous to allow one process to keep the CPU for an extended period, because other processes has to wait that process to terminate or release the CPU. For that reason, first come first served scheduling algorithm is easy to understand, easy to code, and easy to manage, but it will be dangerous to allow large processes and processes with a large CPU burst to get the CPU and never release that CPU, because we want to execute all processes in well-defined intervals to create concurrency. So based on that, we can move on another scheduling algorithm. It's called as shortest job first scheduling. It's a different approach to CPU scheduling based on first come, first served algorithm. This algorithm associates with each process the length of the process's next CPU burst. When the CPU is available, it's assigned to the process that has the smallest next CPU burst. If the next CPU bursts of the two processes are the same, first come first served scheduling is used to break the time. Note that a more appropriate term for this scheduling method would be the shortest next CPU burst algorithm, because scheduling depends on the length of the next CPU burst of a process rather than its total length. We use the term shortest job first because most people and textbooks use this term to refer to this type of scheduling. So for that reason, the good definition is the shortest next CPU burst algorithm. But okay, it's enough to say that this can be considered as shortest job first scheduling algorithm. The shortest job first scheduling algorithm is probably optimal in that it gives the minimum average waiting time for a given set of processes. This part is important. Shortest job first scheduling algorithm is optimal because it gives the minimum average waiting time for a given set of processes. Moving a short process before a long one decreases the waiting time of the short process more than it increases the waiting time of the long process. Consequently, the average waiting time decreases. Here we have an example. So as an example of shortest job first scheduling, consider the following set of processes with the length of the CPU burst given in milliseconds: P1 6, P2 8, P3 7, and P4 3. So we have 4 processes with the burst time 6, 8, 7, and 3 in that order. Using the shortest job first scheduling algorithm, we would schedule these processes according to the following Gantt chart. We know that we have to start with the shortest burst time, so we are going to execute P4 first, then we are going to execute P1, P3, and P2. So the waiting time for P4 will be 0, and the waiting time will be 3 milliseconds for process 1, 16 milliseconds for process 2, and 9 milliseconds for process 3, and 0 milliseconds for process 4 in the right order. But based on the chart, we can say that P4 will be wait 0 milliseconds, P1 will be wait 3 milliseconds, P3 will be wait 9 milliseconds, and P2 will be wait 16 milliseconds. So based on that, we can find the average waiting time as 7 milliseconds. So I have a question for you. If we use first come, first served scheduling algorithm in this set of processes, what will be the average waiting time for this set? Okay, if we use short job first algorithm, the average waiting time will be 7. So what will be the average waiting time if we use first come, first served scheduling algorithm, assuming that the processes enters the ready queue in that order, P1, P2, P3, and P4. An idea? What will be the average waiting time with this set of processes if we use first come, first served scheduling algorithm? Well, similar to that, it will be 10.25 because we are going to start the execute for P1. The waiting time for P1 will be 0, but the waiting time for P2 will be 6, and the waiting time for P3 will be 14, and go on. So based on that, the average waiting time for first come, first served algorithm will be 10.25. So as you can see, we can get a decreased average waiting time if we use short job first algorithm on the same set of processes. So we can make a comparison, a simple comparison, using the same set of processes on different scheduling algorithms. So again, we can say that the shortest job first algorithm is the optimal algorithm. Is that clear? Okay, then. We said that the shortest job first algorithm is optimal. Okay, it's optimal, but it cannot be implemented at the level of CPU scheduling, as there is no way to know the length of the next CPU burst. Because shortest job scheduling algorithm assumes that we know the all CPU bursts of the all processes on the ready queue, but we cannot exactly know the burst time of a process before it starts to execute. Actually, it terminates its execution. So for that reason, okay, short job first algorithm is optimal, but it cannot be implemented at the level of CPU scheduling directly because we don't know, we don't have any direct way to know the length of the next CPU burst. So one approach to this problem is to try to approximate short job first scheduling. We may not know the length of the next CPU burst, but we may be able to predict its value. We expect that the next CPU burst will be similar in length to the previous ones. Okay, we don't know the exact value of the next CPU burst, but we can make an assumption. We can create a model to predict the next CPU burst value based on the previous values. By computing an approximation of the length of the next CPU burst, we can pick the process with the shortest predicted CPU burst. So the next CPU burst is generally predicted as an exponential average of the measured length of the previous CPU burst. We can define the exponential average with the following formula. Let Tn be the length of the nth CPU burst. So it's the actual length of the nth CPU burst. It's already executed, and we know the actual length of the nth CPU bursts. and let tau n plus 1 be our predicted value for the next CPU burst. So we know the previous actual burst of the nth process, and we want to predict the CPU burst time for the next process, for the n plus 1. So assuming that for an alpha, which will be in the bound of between 0 and 1, we can use a formula like that. Tau n plus 1 will be equal to alpha Tn plus 1 minus alpha Tn. So the value of the Tn contains our most recent information, while tau n stores the past history. The parameter alpha controls the relative weight of recent and past history in our prediction. If alpha is 0, then tau n plus 1 will be equal to tau n, and recent history has no effect. Current conditions are assumed to be transient. If alpha is 1, then tau n plus 1 will be Tn, and only the most recent CPU burst matters. So in a common approach, we use alpha as 0.5 or 1 over 2. So recent history and past history are equally weighted. So this formula will be 0.5 Tn plus 0.1 tau n. So we are assuming that we are giving the same weight for the most previous value and the past values. And also we need an initial value for tau 0. The initial tau 0 can be defined as a constant or as an overall system average. So it depends on your algorithm. Here we have a prediction. We have a figure of exponential average with tau 0 is 10 and alpha is 0.5. So based on that, we have tau as 10 here. That will be 10. We don't have an actual tau n, Tn, sorry. So the and let's say that we have an initial value 10 and we get, okay, a real CPU burst 6 here. So based on 10 and 6, we are going to predict the next CPU burst. Okay, so we get the initial value as 10, and then we measured the real value as 6, and we are going to use alpha as 0.5. So our next guess will be 5 plus 3, and we guess that, okay, the next CPU burst will be 8 milliseconds. But in reality, we get 4 here. The next CPU burst get as 4 milliseconds. So based on that, we are going to update our prediction. Here, we are going to get 6 for the next CPU burst. And as you can see, the real value is 6 again. So based on the real CPU burst and our previous guess, we can try to predict the length of the next CPU burst. As you can see here, if the CPU burst is steady, we can make a great prediction based on that. We can create a good approach to predict the real value. And that's how we can use the next CPU burst, how we can guess the next CPU burst to create an approximation of shortest job first algorithm. Because again, shortest job first algorithm is an optimal algorithm, but in reality we cannot know, we don't have any way to know the real burst time of a process which is not already executed. So for that reason, we can create a prediction scheme to based on the previous real execution times and our previous guesses. And that's it. The shortest job first algorithm can be preemptive or non-preemptive. So in the previous version, we created a non-preemptive version, but we can create a preemptive version too, and it's called as generally shortest remaining time first. Instead of shortest job first, we can use a new approach called as shortest remaining time first. But before moving to the next scheduling algorithm, do you have any question? Okay, then. So let's take a break. I'll be here in 15 minutes.